Okay, recording in progress. Let me hide the meeting controls. Hide meeting controls. Oh, why is this thing freezing? Let's see. Hide meeting controls. There we go. All right. So good morning. Today, our purpose is to introduce a material on data frames, which is sort of the star of the show, as it were, pertaining to the Pandas library or Pandas API in Python. But before we begin, the usual administrative bits, the reading by Wednesday, the 22nd, is chapter 5 in the main text, Python for data analysis. Wes McKinney, the author of this book, as I understand, makes contributions or has contributed to the Pandas API. So this should be the best part of this book. Now, certainly, this isn't the only source available on Pandas. There are umpteen many resources available on the web in all sorts of modalities, documents, videos, tutorials, etc. on Pandas. So please don't think that you're limited to this particular text. There are many other sources out there. Homework number 1 will be written. Oh, I say written in quotes, meaning that it's still electronic, but you are free to write it and legibly, and I stress legibly, by hand, and then produce a high quality photograph or scan and include it in a PDF or MS Word document. Question? Yes. Slides, it could be screen recording, it could be video, any way that is comfortable for you for making a presentation. Yes, absolutely. I might have forgotten to say, I think I said, did I say presentation in there? I think I might have. So some people choose to do the voiceover on the PowerPoint slides or whatever version you use. Some choose to have video screen capture. If you're on Mac OS, you can use QuickTime to record the screen. Some choose to do it that way. So there's no one way to do it. But if you do the recording, if you could kindly include that particular recording of your presentation along with the slides. Yeah. Other questions? Yeah, sure, sure. No more than 5 minutes. And that's a practical thing because it shouldn't take more than 5, but also the size of the recordings get really big really fast. And there's an upper limit on the uploads that you can have on Moodle. And so no more than 5 minutes. And it could be 5 minutes for you, could mean 10 slides. It could mean 5 slides. When I say slides, I mean the content containing slides, not like the title slide and conclusion and stuff like that. Any other questions? No? Now, of course, it's really important as part of our conversation for this course on articulating your results. And so this is just the beginning of what will ultimately be the presentation for your final project. And so for this class, our final exam is a comprehensive data science analysis problem that's fairly open-ended. And for that, you'll be giving a presentation. Okay, so there's a whole reason behind this. So homework number 1 is due this Wednesday, the 22nd. Hard to believe February is almost over. We're just celebrating New Year's not that long ago. I did finish uploading all the comments and everything for project number 1. Project number 2, now that I've figured out some stuff with Canvas, should be getting graded definitely by or before the end of this week, by Friday. One of the issues in Canvas certainly doesn't affect you. Maybe it does a little bit. In Moodle, when you give comments, you can save the comments as draft and re-edit them, and you can have formatted text, like use different fonts and bullets and stuff like that. But in Canvas, it's more just like free-form text, which is harder to use. And when you submit these comments, it's more like a text message. You can't re-edit them, which kind of is problematic if you like to review things. So some issues that I saw recurring in some places, some students forgot to include certain required components with the submission. In your excitement for handing in the assignment, please take pause to look at the submission instructions and make sure that everything that you're being asked for is being submitted. Make sure to claim those points that you've worked hard to earn. This class has people from various majors, and data science, by its nature, is an interdisciplinary study or area of study. And so we have all sorts of different folks in the class across different majors, including non-science majors. And for that reason, we have varying degrees of background in things like data structures and all sorts of other concerns. And so I've left some notes for folks. Please make sure you're reading the notes that I enter in for you. If there's a message for you, please make sure to read that. And I'm not going to talk about what those messages are. All right. Any questions? No? No questions? All right. For the most part, everyone did very well. That's pleasing to see. And I read all of the reflections and look at all of the notebooks because it helps me to get a sense of, what people are focusing on, what you find useful, and that material from last time, I actually do use to help shape the course in the next offering. So you're benefiting from the reflections and stuff for people from last year. Okay. Any questions? No? No questions? Okay. So last time when we met, to refresh your memory, we talked about variable coupling, and I promise this is the last time I'll try to use a Lionel Richie reference in this course. I think it's funny, but I don't know. Anyone know Lionel Richie? 80s are okay. Thank you. At least two. All right, great. So nonetheless, we talked about this idea of variable coupling. And we gave a different definition for it that we explored, one based on statistical linkage, not the linear linkage that we talked about with covariance and its normalization correlation. And so we looked at this idea of independence. And with this idea of independence, we explored this definition as looking at the value of the information for that particular variable or event that you're conditioning on. And we said that when you know some information, given B, event B, or random variable, or measurement B, that does not change the probability of A. And we said that when you look at this on the Venn diagram, oftentimes people pose it as having these two events carved out of our sample space omega, our events A and B, as being non-overlapping. Absolutely, that is true. But the richer definition, which is actually true, is that it means that the probability, this rate, does not change. And so with that, we talked about this intersect region where A and B overlap, carving out common objects from our universe of consideration, sample space omega, being the same proportion to B as the original A event to our sample space omega, our universe of consideration. Any questions about that? Jar your memories? All right. And so we then went through a proof, and I'm not going to repeat the proof. I'll direct you to the recording from Friday. If in some cases, or many cases, it's a little bit more difficult to think about the probability of an event, it's easier to think of the complement, the probability of that event not happening. And that's just in general solving. And so one of the important facts is to demonstrate that if two events A and B are independent, meaning in this case, their co-occurrence is equal to the probabilities of their individual occurrences, then so too are their complements also independent. And so we made a bunch of assumptions and we used the fact for total probability in solving this and proved it last time when we met. Any questions? No? All right. So then we took our definition for conditional probability and we use the fact that the co-occurrence, the ANDing, the overlap region between two events is commutative. And so if we were to write the probability, let me choose my color here. How about this blue? I'm a fan of blue. The probability, oops, the screen just froze. That's not good. There we are, okay. Something is going awry. The probability of A at the same time B is equal to the probability of B and at the same time A. And because we're referring to this intersect region here in the middle, it doesn't matter if A goes first for the and or B goes first. And so using this, we took our definition for our two conditions, probability of B given A on the left. I'll just kind of write that as equation one, and equation two on the right, probability of A given B. We filled in our definition and used the fact that and is commutative. And then we did a little bit of algebra and we came up with this expression at the bottom, probability of B given A, as a function of ultimately probability of A given B. And so we call that Bayes' rule. And we said that Bayes' rule is particularly important because it allows us effectively to manufacture this condition given A. And so when we have a condition, it's almost like saying, what if I observed that A event to occur or to be true? Now, given that it's true, that changes your universe of consideration. Yeah, but we can manufacture that condition pretending that we observed A using some observation given B. Okay, does that make sense? And so this idea of manufacturing conditions using other conditions given B is really, really important for all sorts of applications. But one of the confounding things in this expression is here in the denominator, we have probability of A. Well, if we don't know A, how are we going to talk about its probability? Okay, that's a valid point. So we then used this idea of total probability. And to motivate that, we looked at a Sicilian slice, so to speak, slicing of our sample space omega. And we took this partitioning and we defined it as a set of non-overlapping slices, or so-called B slices. And these B slices are of a particular form that's very special. They fully cover all of the sample space omega, collectively exhaustive, and they're non-overlapping. They're pairwise independent. And we said that when you do this, you can take an arbitrary event, A, as we see here, and we can represent A or decompose it as the bringing together or the union of all of those places where A overlaps some of B slices. Now, of course, here, if we looked at slice B sub K, my pen is freezing again. I don't know why that's happening. Okay, let me just talk and not use the pen. So if we look at, say, B sub K, the kth B slice, we know that it does not overlap A, so that's empty. It contains no objects from our universe of consideration. But other B slices, they are overlapping with A. And because the B slices are non-overlapping, we can compose an arbitrary event, doesn't matter how complex it is, by just taking the union of all of those parts where A overlaps some B slice. And so said differently, we have our expression here, probability of A is equal to the sum of all of these overlap regions between A and each of these B slices, which I tried to depict on the previous slide. Okay, does that make sense? Any questions during your memory on Friday? So now we then can take this expression for A intersect B, and we can substitute a fact that we call the product rule as a consequence of that Bayes rule development and rewrite this intersection, probability of A intersect each one of the B slices, as A given the B slice times probability of the B slice. And so we imagine then if we only had two B slices, the first one we would call B1, second one we would call B2, or we could call it B and B bar. And as such, using this representation, our sum and the product rule, we can write probability of A in terms of our chain rule, our product rule between A given B times probability of B and probability of A given B bar times probability of B bar. I don't know why this pen is freezing and the video is freezing. I'm not expecting this. So I have no idea what it's going to look like afterwards. Excuse me. That's weird. All right. Any questions? No, this is kind of throwing me off a little bit. All right, there we go. hopefully let me, there we go. Oops, no. All right. So with our idea of these B slices, our so-called total probability, we can now change the denominator from probability of A to the sum of all of these overlaps between the B slices and our arbitrary event A. And when we do that, for the case where we have two B slices, B and B bar, the denominator here, you'll notice my condition is now only in terms of things that are not A, things that are B or B bar. And so here, because this is an equivalent expression, we can now manufacture what it means to have observed something called A, be that a random variable or an event, but we only use conditions on B in order to manufacture this idea of having seen or being given this information A. Okay, any questions? Does that make sense? So then we said, okay, a reasonable, this is just a reasonable question to want to ask is why should I care? Okay. And we referred back to the dog example, and we said that each dog can be represented as a random vector, an instantiation of our random variables. And it's freezing again. This is weird. Nope. Something's definitely going on with the cloud services. All right. I apologize again. We said that each dog can be represented as an instantiation of a random vector. And here we have 6 of them. And when we use this Bayes rule, here we can use single random variables, variable B, probability of B, given variable A, or we can use the position of B and A with a conjunction of a vector of variables. And so in that case, oh my. All right, computer. Yeah, something else is, and I'm plugged into the wired network, so I'm not sure. Let's do this. It's like pausing every like 1 or 2. Okay, let's try this again. Now it froze again. Check. I don't have a mic either. All right. So here we have taking the position of probability of B, we have our variable C for coat, and taking the position of that condition given A, we have all the other variables, length, width, height, and weight. And so plugging in to this expression for Bayes' rule, making the assumption of total probability, we can now use our left-hand side, left-hand side of the expression. This is going to be comedic today. Our left-hand side of the expression to do classification. And so essentially, in practice, you drop the denominator of the right-hand side of the expression, and we give special names to them. Left-hand side is the so-called posterior distribution, and we have the symbol meaning is proportional to, and we use is proportional to and not equal to because it's no longer a proper probability, but what they're concerned about is the idea of the highest degree of belief. And so on the right-hand side, we have 2 terms. We have the probability of that vector consisting of length, width, height, and weight, given the coat, that particular coat. That's called our likelihood function. And then we also have the so-called prior distribution. Now, everything to the right of that is proportional to symbol is something you can calculate from data. And we're going to use data frames to do that, hopefully on Wednesday's practical session. Okay. And again, I apologize for all of this, like starting and stopping. You're not seeing what's on my screen. It's different from what's on the big screen. I have the video going, I have my pen active, and it's like freezing. And so I do something getting ready to talk about the next slide, and it doesn't advance. So it kind of throws me off a little bit, and it's freezing again. All right, so why don't we jump in? So today, we're going to talk about data frames. And a data frame is a high-level data structure that is the star of the show, so to speak, of the Pandas API. And a data frame is very different from NumPy. NumPy is fairly low level, and it has support for multi-dimensional arrays. And how you define a dimension is another level of nesting for putting an array in the position of another array. And so in Pandas, we said, okay, you start out with a one-dimensional array, and in each position, if you place another array object, that inner array is your second dimension. So you can go to 3 dimensions, of course, by having another inner array, and you can arbitrarily increase your dimension and populate your arrays up to, well, theoretically, the limits of memory that you have on your machine. And as you saw, along with Pandas comes the slicing syntax and semantics. And I kind of like NumPy over regular Python arrays because it's more pleasing to me when you do the array index to have each one of the dimensions in a comma-separated list referencing the array variable. Okay, and certainly with NumPy, the value of NumPy is associated with all of the matrix types of operations that you have, both things like trigonometric as well as exponentiation, as well as things like matrix transpose and flattening that we had talked about, at least the flattening and the transpose. Okay. Any questions? No? And so for Pandas, that high-level data structure that you traffic in is called a data frame. And that data frame is a 2-dimensional data structure. So it's a table. But what really gives Pandas and therefore data frames its power are all of the APIs that you can call on these tables. And so this data frame is high level. And it's also well-tuned for so-called tabular data, but also for time series. Representing constructs in time is a lot more easy to do in Pandas, specifically data frames, and more correctly in a series. And so with time, you have APIs for calculating date ranges, for calculating date differences, for incrementing on arbitrary boundaries, whether it's seconds, weeks, months, quarters, and you name it. Pandas API can do it. You can also so-called align your data in Pandas. Oftentimes, when you collect information, particularly from sensors, you might have one sensor, maybe that's giving you a measurement 2 times a second, and another that's giving you measurements, say 10 times a second. If you're going to put all of that information in a table format, you have to make a decision about which boundary you represent time along, and Pandas has APIs allowing you to do that. In addition, because the world is not perfect, oftentimes when you collect measurements, and you saw this in the Bureau of Labor and Statistics data for one of the food items, sometimes you're going to have missing data. And so that typically corresponds to that for whatever reason, maybe a sensor failed, or maybe that information wasn't available for that particular reporting period. And so when you handle so-called missing data, you have to make a decision about what you're going to do. But more importantly, that decision that you make is going to impact what that data becomes after you transform it. And so some example decisions that we'll look at, you could take a row of your data from your table. You can imagine it's from a CSV file, and you can decide if there is missing data, you go ahead and you drop that particular row of the table. You just exclude it from consideration. Now, of course, when you do that, you're changing the distribution because you're removing data for those entries that are not missing. Another approach you could do is maybe you're going to replace it with a value that you calculate. Well, how you calculate that value is also going to impact the resulting distribution of your data. And so one popular approach is to replace missing data items with the mean, the center of that distribution for that particular random variable. Okay. Any questions? No? All right. And so another thing that Pandas affords you is the merging and joining of data sets. And so we saw that when we had the different food items, and we kind of did that the manual way with CSV read, and we did some matrix transpose, and we inserted them as columns in a consolidated data set. Pandas has a very sophisticated way of putting together different data tables. And so that's probably the most weird part, so to speak, of Pandas, because you can do things ranging from SQL joins to intersections to all sorts of behaviors. And so certainly we won't cover all of the different variations of the way you can merge and join data tables. I'll leave that to you to explore on your own, but we'll certainly cover some major ones and have opportunity to make use of them in practice. Okay, any questions? No? All right. And so this is a data frame, all right, not very sophisticated, at least pictorially. And so like a table, kind of more like a CSV file, we have a set of rows and we have a set of columns. Now in Pandas speak for data frame, the columns are implemented in a particular data structure, something called a series. And we'll talk more about what a series is. And the rows, okay, the rows represent entries within each one of those columns. And so each of those entries, in this example, we have, and I'm afraid to use the pen, we have the 0th entry, which represents the 0th row, or the 0th entry in each one of those columns. We have the next one, the first, the second, the third, the fourth. And so one of the things that we'll find today is that each one of these entries, the 0th, the first, the second, etc., are offsets within each one of the columns. And so it's treated as an offset within each one of the series representing each one of our columns. And now each one of these row numbers is given a default name, and that name is called the index. And so when you instantiate or create a data frame, one of the things it will give you is a name associated with each row. Now that name can be the default name, and it'll give you a numeral corresponding to the offset within each column, or you can tell it to use names that you supply. And we'll see some examples of that. Okay, any questions? No? All right. And so one of the important things when you're dealing with any data structure is to understand how it's built up underneath the covers, because that will help you understand what's going on should things go wrong. And so inside of a data frame is a Python dictionary, and a dictionary is a data structure that consists of so-called name-value pairs. And so here, this dictionary, you'll notice, it uses open and closed curly brace. It does not use square brace. So it's almost like an array, but it's not really an array. Each one of the entries in this dictionary consists of two components, a key, which is typically a string, separated from the value, which can be some Python object, and it's separated by that colon. And so with this, you can specify these so-called name-value pairs, and this dictionary is nothing more than an array. I'm just kind of using the word array very loosely, an array of name-value pairs. Now, the power of this construct has to do with the so-called slicing, if you want to call it that. In this example, we have a variable of this dictionary. So again, we have the open, close, curly brace. And then each one of the keys, we have brand as the key for the first item, model as the key for the second item, and year as the key for the third item. Now, these particular values for this dictionary, well, the first two values are strings. We have Ford for the value for this brand key. We have Mustang for the value for this model key. And then we have a numeral here. We have 1964 for the value associated with year. And so with the dictionary, you have this association of names to values. The name is a string, but the value can be an arbitrary object, whether that's a string, whether it's a numeral, but it could also be a list. And so one of the things we could do with this particular dictionary, is if we wanted to print out the associated value, say forward, for that first name value pair, we would access the dictionary as an array using array access notation, but we would give it the key associated with that particular item in their dictionary. Does that make sense? Any questions? No? And so if you're curious underneath the covers, it's using something called a hash lookup. If you for the computer science folks in the class. Okay. Now we said that this value can be a Python object, not just a string or a numeral. And so this is a data frame. A data frame is nothing more than a list of dictionary entries. But the object in the case of a data frame is not a simple type like a string or a numeral, it's a list. And so here in this data frame, we're constructing our data frame using the Pandas API, and that's not the only way you can construct it. And you'll see here, we have a comma separated list of key value pairs. So here's the first item called name, that's the key, and the value is an object, yeah, but that object is an array. It's an array of what? It's an array of strings. Now we also have our second item here, the key value pair. The key is age, it's a string, and the value is a list of numerals, 22, 35, and 58. And then lastly, this third key value pair has sex, and the value is an object, and it's an array, and it has male, male, and female. Any questions about this? Does that make sense? And so underneath the covers, a data frame, you can construct it many different ways, but a data frame is really nothing more than a list of dictionaries where it's a mapping between a key and an array object. Okay, any questions? No? Does this make sense? Now, of course, if you were to fire up your Jupyter notebook, which we will do, hopefully if time permits, and you take a look at the data frame you've constructed, you'll notice this tabular depiction of that data that we specified. And you notice here, this first column, it's given a column header, and all of the column headers or variable names you could think of as random variables are the key values that you have for your data frame. And so here we have name as the first key, age as the second key, sex as the third key, and you'll see here a column header name, age, and sex are the column headers when we visualize it in something like your Jupyter notebook. Likewise, you'll notice here all of the entries, if we have the 0th entry in our name array, oops, I just froze again. It's Brond, Mr. Owen Harris, and then we have 22 as the corresponding 0th entry, and we have male as the corresponding 0th entry in that next column. You can see as you go across the first row, we have that Brond, Henry, Owen Harris, 22, and male. But you'll notice this extra column here, that 0th column, it has offsets, it has numerals, the 0th offset, the first offset, the second offset. Yes, that is a row number, but in a data frame, that's the so-called default index. If you do not specify the index for the data frame, it will insert one for you. It's default, and that default is going to be the number representing the offset within each one of the lists corresponding to your columns. Does that make sense? Any questions? No? All right. And so a data frame is nothing more than a dictionary that contains lists. And it's really important that all of the lists have the same rank, the same number of elements in them. If you have a list that's bigger, well, it's going to need to construct it for you, and it's going to fill in a default value, something called the empty value, which we'll talk about in a moment. And so the keys for the dictionary represent the column headers. You could think of them as the variable names for each column, if you think about it as a joint probability over it. And then the values are the column data. The values are arrays, and those arrays can be mixed type. You can have strings as one column, you can have numerals as another, you can have Boolean, etc. And so in this case, we have text data for the name column, we have numerical data or quantitative data for the age column, and we have text data for that last column. Okay. Any questions? No? Make sense? All right. And so data frame is two-dimensional. I think I just said this. This is a duplicate slide. And you can have mixed types, including floating point, categorical, you can have strings, you can have booleans, you name it. There are arbitrary objects that you can have as your column information. Okay. And so these columns, how you access a column within a data frame is by using the array access notation, using that variable to which you've assigned the data frame. Now, I'm mirroring the umpteen many examples that you find online. They always use a variable df for data frame, but you don't have to do that. It's just trying to make it comfortable based on what you see online if you search around for it. And so in this case, we have three columns. One's called name because that first key is called name. One's called age and one's called sex. And imagine then if we wanted to access the column information for that age column. And so we take our variable df for data frame and we use our array access notation, but instead of giving it slice notation, we're going to give it the key name. Now, it's really important that when you give it the key name, capitalization matters. So if I had age with all lowercase a, lowercase g, lowercase e, it would say, I have no idea what you're talking about. It's really important to make sure the case matches up. And so when you do this type of slice, let's call it a data frame slice, it'll give you back all of the elements in that particular list. In this example, it'll give you back the numbers in the list 22, 35, and 58. Now, of course, when you do this, you're going to get back information, but this information is going to be a different data structure from an array. It's going to be wrapped up inside something called a series. And this series you can think of as Pandas's version of a one-dimensional array. And so a data frame, yes, it is a list of dictionaries. It is a dictionary of lists, I should say. But when you slice out one of these columns worth of information from the data frame, it's given to you as a series object. And the reason for that is that all of the other APIs that you can use, it's tied to the object itself. And so the way to do that is to take your array from that column, put it in this other object called series, and now you have available to you all these other very useful functions that you can call. Okay, any questions about this? Does that make sense? Yeah. All right. Now, I don't know if you had data frames in 120. No, some have, some don't. Okay. Okay. And so, like a dictionary, the access to each one of these columns is just done using the key value. So it kind of looks like an array, and it also looks like a dictionary. Okay. All right. So here's a series, and I've purposely, in this set of slides, I construct it just because it's a good way to show you what's inside of it instead of reading it from a file, which you can absolutely do. And so in this case, we're going to construct a series, and there's absolutely nothing special about a series. It's just a data structure, and you can instantiate or bring into being, into memory, an instance of this series object. And so let's assume we imported pandas as PD, and I call PD.series. What that's essentially doing is saying, take this code for series, go ahead, construct one, put it in memory, and stuff it full of information. In this case, the information we stuff it full of is an array of numbers. That's going to be our data. But you notice here, the second parameter, index equals, and we have a comma-separated list of strings, of characters in this case. Now, if we did that, okay, well, we just said that a series is the representation for a column in a data frame. So you could construct a series and say, go ahead and insert this as a new column in your data frame. And so rather than doing what we did in project number 1, project number 2, it's a lot easier in data frames. But the reason behind having you do it with NumPy is so that you'd appreciate what the algorithm is doing in the data frame. So nonetheless, we construct our series, we give it our array of data. So that's going to be the array object portion associated with the series. And then the index is going to be that default label that it uses. Again, if you don't supply a label, it's going to use the default, which is going to be the numeral representing the offset of each one of those values for the underlying array in that series. And so here, if we say go ahead and show me the contents of that series, it says index 0 is A and has a value of 1. Index 1 is B. It has a value of 2. Index 2 is C and it has a value of 3. Now, essentially, you're replacing this default index, but I just thought I'd kind of verbalize what the default is and what those replacements are in this case. And so it doesn't matter what these values are. What matters is that you can replace it with whatever strings you want to describe what these offsets mean, if that's meaningful for the problem that you're working on. Any questions? Does that make sense? No? Still Monday morning? All right. Okay. All right. So you can create these series yourself. Another way you can create the series is using a dictionary. And so in this case, we create the series. So we bring into memory the series object and we give it information with which to construct itself. And so here we give it a reference to a dictionary. Now you notice here, we're not specifying an index like we did on the previous slide. But what it does when it sees a dictionary, the runtime says, okay, well, this is a dictionary, not simply an array. So it goes ahead and it takes a list of the keys and it uses those keys for the dictionary as a replacement for the default index. And so here we have our dictionary D, and we have the first key value is A, and its corresponding object is 1. Our second key value is B. Our corresponding object is numeral 2. And then lastly, our third key value is C, and the corresponding numeral is 3. And so when we construct it, you'll notice here on line 3, we have index A, index B, index C have a value of 1, 2, and 3 corresponding. And so there's more than one way to get to that. Which one is better? It just depends on what your approach is and what you're after. They're both equivalent in terms of the end effect. Any questions? Does that make sense? No? All right. And so the useful functions that you can perform on the data frame, there are several, in object-oriented programming, it's called a method. There are several functions that are associated with this, this object. And when you call these functions, it assumes the underlying data with which this particular object was constructed. So that, if you want to take for example, the mean of some value, why not take the mean of that object and know that the data inside of that object is what you're going to be computing the mean over. And so, for example, here, we've constructed a data frame. And again, a data frame is a dictionary of lists. And so we have 3 entries in this dictionary. We have the name value, and the object is an array. It's an array of strings. We have the age value, and the object associated is an array. It's an array of numbers. And then we have sex. The object is an array, male, male, female. And so with this, okay, we slice out the age column, and we return back a series object. Again, you return back a series, and that series is an object that contains the list inside of it. But because it's a series, now we can call those useful methods on that series. Now, in this case, we get back a series called ages, and it contains all of the contents of this array, 22, 35, and 58. So some of the functions that we can exercise, it includes visualization, it includes summary statistics, it includes plotting, all sorts of things. You name it, it's there. In this case, we could say, give me the maximum value in this underlying array inside the series. We would say, give me the mean, or this other one, which is pretty useful, interpolate. And I'll talk about what interpolate means in a few slides. Okay, any questions about this? That makes sense? And so here, another useful thing you can do on the data frame, and again, a data frame is a table where each column is a series, and underneath the covers, it's just a dictionary, a set of name value pairs. And so if you say data frame describe, it knows what the types are, whether it's numerical types or string types, and it'll go through all of its columns and say, okay, if you are a numerical type, I'm going to compute popular summary statistics on you. And so this method or this function or API call called describe, if you call describe on the data frame, it's going to loop through all of the series contained in it. And for those series that are numerical, it's going to compute these summary statistics. And so here in our data frame, if we go back one slide, the only numerical column or series is age. And so if we say data frame describe on that same data frame, it's going to tell you which particular column it was. It's the age column, and it's going to give you various summary statistics like the mean, standard deviation, min, max, as well as the quartiles. Okay. Any questions? Does that make sense? Yeah. So suppose we had two different numerical columns. And let's say we had age and we had, I don't know, temperature. Maybe it's a medical database or something like that. If we did data frame describe, we would see another column next to age for temperature, and it's going to give you all of those same summary statistics for that temperature column. Okay. Any questions? Does that make sense? And so, yes, you use NumPy and you call these functions for summary statistics on each of the columns worth of data that you sliced out of the NumPy array. But the data frame does it for you, but it's important to appreciate what it's doing before you just memorize the API. Any questions? Yeah? All right. So let's take a look at input-output. When we dealt with project number 1 and project number 2, we looked at CSV read. Now, this is a particular CSV file, and this represents some data from the manifest of passengers on the Titanic. I keep saying Titanic, the Titanic cruise liner. And so, like a CSV file, we have a comma separated list of strings as our header, and that kind of almost looks like the column names for a data frame. And so if we direct your attention to that first data containing row right after header, you'll notice here there are two commas, but there's no value here, right? That's a missing value. Now, when you read into memory and there's a missing value, you can't just have nothing represented on a computer. You have to have some placeholder that says this is missing. In similar fashion, the invention of zero is a human invention. You can't go out in nature and see a nothing, right? You can't. So in similar fashion, anytime you have a missing value, when you read it into memory, you have to have some placeholder to represent that. And so for numbers, this construct, not a number, NaN, is used to represent a missing number. It's different from infinity. It's the nothing number, a number that doesn't exist. And so this not a number, it looks like a string, but it's not really a string. It is absolutely a number. And when you have these not a number entries, you have to make a decision about what you're going to do with them. Because, for example, if you take the sample mean, well, there's a default behavior that says ignore those entries that are not a number. But if you want to do all sorts of calculations, you can't make a calculation on a non-existent thing, right? And this not a number is a replacement for that. Now, if you have strings, depending on the system and the API you're dealing with, there are different ways of representing strings. You could use a null string, which is just an open close quote. But if the string doesn't exist, very often in Python, sometimes, they use this thing called the none value. It means a string that doesn't exist. And a string that doesn't exist is different from the empty string, right? It's very different from the empty string. But some APIs will just treat the empty string as the nothing string. Okay. Any questions? And so anytime you're dealing with data, absolutely, the real world is very imperfect. You're looking at medical records. Maybe that measurement wasn't made. Maybe there was a glitch in the value and it just didn't fill in a certain value. You still have to do something with this and make a decision. And so there are APIs in the data frame and called fill_NA, which takes a parameter and it allows you to specify what value you're going to use to replace these not a number entries. You could decide, if I iterate through all of the rows of this Titanic data, I'm going to exclude from my data set all of those rows where I have a not a number entry or missing value. Now, again, if you do that, that's going to change your distribution, and any statement you make on this altered data set is going to be different from what you could say about the full data set. Okay, any questions about this? Make sense? All right. And so in Pandas, you have a lot of support for a lot of different file formats. Like we saw with the CSV reader, you can take a file in a particular format on disk and you can bring it into memory. You can so-called ingest that data, or you can take that representation from memory and you can send it out to disk. You can export that data. And so Pandas supports all sorts of file formats. You name it, they support it. Like JSON, JavaScript object notation. It's a particular file format, and it's very useful for, among other things, representing the on-disk representation for objects that are in memory, right? That's what it started out as, but they use it for arbitrary data representation. If you've taken or are planning to take the databases course, SQL, standard query language, is a whole syntax and semantics for manipulating data in large databases. So you can bring together lots and lots of data, and you can link parts of the data to other parts of the data. Pandas supports it directly, at least bringing it into memory in the form of a data frame. CSV, you see here, is supported, and you can both read the CSV, bring it into memory, and when you read it, what the data frame goes ahead and does, it says, okay, when I create my dictionaries, I'm going to set as the key values all of those pieces of text that you had in your header row. And so it will do that very nicely for you. Okay. And so in this case, with a data frame, when you read in a CSV, you don't have to create an iterator and throw away the header line to deal with the data. It'll automatically convert it for you to the key values associated with the column names for each of the series that form your columns. Any questions? Does that make sense? Now, regardless of the file format, and we'll have a chance to use Parquet files, which is a binary format that's particularly useful for large data sets. Regardless of the format, the scheme is read underscore followed by the name of the format. So if it's to read a CSV file, it'll be read underscore CSV. If you're going to write a CSV file, it'll be to underscore CSV. If it were Parquet and you're reading a Parquet file, it'd be read underscore Parquet. And if you're going to write out a data frame to a Parquet file, that binary format, it'll be to underscore Parquet. And so why isn't it write underscore CSV? That's a great question. And I always kind of half jokingly say maybe the person who implemented it missed the engineering meeting that week. All right. It just strikes me as weird, but I suspect they want to be consistent. And maybe write underscore SQL doesn't read well. I'm not sure why. Why is it two? If anyone finds out, that'd be some nice trivia to know. All right. So nonetheless, here we import pandas as PD, which is the style that you see in all the examples online. And you have pd.readcsv. You give it the name of the CSV file. Now, of course, here I just have titanic.csv, but if I had an arbitrary file path on the file system, I would give it the file path to the file system. So in this example, it assumes wherever I'm running my Jupyter notebook that the CSV file will be alongside it in the same directory. Any questions? Does that make sense? So now in this case, instead of like on the previous slides, where I constructed the data frame as an array of a dictionary of lists, I'm reading it in from the CSV file, and it's important to have that CSV file properly formatted. And so once I read it in, I get back a data frame. In this particular case, I'm assigning this data frame returned by pandas read CSV. I'm assigning it to a variable named Titanic. And so now if I tell it to show me this data, if I just type it on the line, it'll just go whooshing by and show me all of the entries. And you notice here, cabin is not a number for that 0th row. And if I go back to the first few lines here, there's no entry here. Okay. And any questions? Does that make sense? Okay. And so in this particular case, the Titanic file, and I'll post it on the course Canvas site, it has 891 rows and a total of 12 columns. So you can compute the shape, you can extract arbitrary columns from it, and you can do all sorts of other interesting things that we'll talk about in a few moments. Okay. Any questions? No? All right. So, and it just froze up again. Um, okay, and so if we had a data frame in memory, for example, the one that we constructed, now we would just say data frame reference 2 underscore CSV. We could give it directly a CSV file to write, file name.csv, or we could give it a fully qualified path to someplace on the file system. Now, it will work only if you have what's called write permissions for that directory. So if you're on a multi-user machine and you say, I want to write this to this location where the operating system's executables are located, you don't have permissions to write there. It's just because you can specify a file path doesn't mean you can write to that file path. Okay. Any questions? Does that make sense? And so here, one of the things, methods that you can call on your data frame object, another method, is a so-called head method. Sometimes you just want to take a quick check to look at the first few lines or the last few lines without having all 891 rows go whooshing by on your screen. And so if you exercise the head method, you give it an integer, and it'll only, in this case, display the first 8 entries from each one of the columns. And so you notice here, there's a default index, and we start at index 0, representing offset 0 in each one of the series, representing the columns information. And that last default index here is 7. So 0 through 7, that's a total of 8 entries. Any questions? Does that make sense? And so likewise, you can give it the tail command. It'll give you the last n rows. And if you give a negative number, it'll give you all rows except for the last n. So if I said head -5, it'll give you all but the last 5 of the rows. Okay. Any questions? No? All right. So now, let's see what I have here next. Frozen again. Example operations. Yes, all right. So the visualization APIs are also tied in to the data frame and the series objects. And so here is an example data frame. Again, it's a list dictionary of lists. And so we have length is our first key, and here's our list associated with it, 1.5, 0.5, 1.2, 0.9, and 3. And then we have width, our other column information. That's the other key. And then it has its array data. And you notice here the rank of these arrays are the same. They both have 1, 2, 3, 4, 5 entries in their respective arrays. In this case, for the data frame, we're replacing that default index with these strings, pig, rabbit, duck, etc. Now, if we create that data frame, now we call the histogram method on this data frame, and we can specify optionally what the number of bins is. If you don't specify the number of bins, the default is 10, and we'll get a histogram. And in this case, the histogram is for every numerical column in the data frame. And so this does it for you for free. You don't have to iterate over things. You don't have to slice. You don't have to call histogram twice. As long as you have numerical columns, it's going to assume that your histogram is over those particular columns whose information type is amenable to plotting as histogram. Okay, any questions? Does that make sense? Okay. So you have one histogram per series or per column. Another thing you can do, and this is pretty interesting, is you can compute the min and the max of the rows or the columns. And so in this case, again, we have 2 columns. One is called consumption, and the other is CO2 emissions. And each one of these is quantitative data. The arrays are the same rank, and they have numerical information in them. The index is pork, wheat, and beef. And so here we're replacing the default index. Pork is going to be the name for position 0 in the data frame. Wheat products is going to be the name for position 1, and beef is going to be the name for position 2. So if we create this data frame, and I'd really like to bring up my pen. If we create this data frame, we'll notice on the left-hand side, if we visualize it, we have pork followed by wheat products followed by beef. But then in the next 2 columns, we have consumption and we have CO2 emissions. And so here, going from left to right, in the consumption array, we have 10.51, 103.11, 55.48, and going down that consumption column, we have 10.51, 103.11, and 55.48. And so here we can rename the default index from zero to from numerals rather to particular strings if it's important for your application. And so with this on the data frame down below, we call ID max. And what that ID max does, it says, okay, well, I'm going to look at each one of the columns, my numerical data, and I'm going to return back the index value associated with the maximum entry for that particular column. And so if we go down the consumption column, this is like, I won't even try the pen anymore. I really wish I had a way to point to it. I can use the laser. So if we go down the consumption column, we say, okay, the maximum value is 103. Which index is that? It's the wheat products index. So here we have consumption. The maximum is wheat products. If we go down the CO2 emissions column, the maximum entry is 1712. That corresponds to the beef index. And so it returns back beef. If you were using the default index, it would return 1 here, and it would return 2 here if you're using the default index. And so here, it will go down each column. It'll go for each column, it'll go down the rows or down each entry in a column, and it'll return back the row that has the maximum value. And you can do that for minimum value as well. Okay, any questions? That makes sense? And you can also switch which axis it searches down. If you say ID max and you say axis equals columns, what it will do is go to each row and it'll say, okay, well, if I start out with pork for that 0th row, it'll go to the first column and the second column and it'll say, okay, which one of them had the largest entry? 37.20. All right, that happens to be CO2 emissions. So for pork, the largest value is CO2 emissions. For wheat products, if you go across, the largest value is for that 0th column. That's consumption, so it says consumption. And then for beef, and you notice there are 3 entries here, it goes across and it says, 1712 is the largest value. That's the CO2 emissions column. And so you can change the axis across which it searches when you're doing ID max, and you can also do for ID min. But if you don't specify the axis, the default is the rows. Okay, any questions? Does that make sense? So there are so many things you can do with a data frame. I can't possibly cover them. We'd probably take a whole semester just on pandas, which would kind of defeat the purpose of the course. All right. Another thing you can do is insertion. Just like how we were doing an insertion for the month date or the month year column for project number 1. And so here we have a data frame, and this data frame has 2 columns, column 1 and column 2, and each list has a rank of 2, so 2 elements. And in this case, we're using the default index. And so you notice here on the left-hand extreme, we have index 0 and index 1. That's what you get if you don't specify your own index. And so here, you'd imagine, you might want to insert a new column. And so we use the insert method on the data frame object, and we give it a couple things. We give it the particular column where we want to insert, position 1, and remember it's zeros based. And so here, position 0 is here, position 1 is here. We're going to insert before that one. And so here, we do the insert, position 1. The name of the key is going to be new column, and the list is going to be this 99 and 99. As a result, you'll notice here, new column is now in this position, and it has new column as the column name, the key value, and 99 and 99 as the values populating the list of rank 2. Any questions? Does that make sense? So because data frames take mixed types natively, you could read the CSV that we had from project 1 into a data frame. You could construct your data array and just insert it as a new column in the data frame and then write it out to CSV. Okay. Another thing you can do is you can have duplicates. You can have duplicate key names. Now, it's not recommended you do this, but if you might have a reason to do it, Pandas lets you do that. So with this, you add another option with the data frame insert called allow duplicates. And so here we'll say insert in position 0, the key column 1, and there's already a column 1. The value is 100 and 100, and allow duplicates is true. And so now you have 2 columns with the key value column 1. So what do you do if you want to access one? You have to ask the data frame by position, give me the column at this location, location 0, location 1, or location 2. Question? I'm sorry? To have duplicate entries? Sometimes when you do joins, people like to have duplicate names. It allows you to do it. There's no one prescription about when you would use it, but they don't restrict you from having duplicate names. And so maybe one thing is an alias for another. It all depends on your application. There's no like scientific reason to want to have duplicate names. It just lets you do it if you choose to. The default behavior is to not have duplicates. But if there were a reason you wanted to have duplicate column names, it lets you do that. Some of the more esoteric joins, having duplicate names is useful when you want to align stuff. But there's no rule that says you have to have duplicates. And you can accomplish without duplicates everything you can, but it doesn't restrict you from having duplicates, if that answers your question. Any other questions? No? All right. So another important method you can call on the data frame is so-called interpolation. And the interpolation I'll show you here is linear interpolation. And linear interpolation is not the only type you can make. And so here we have a data frame, and this is to kind of show you another way of constructing a data frame. One thing you'll notice here is that each entry here in my data frame, I have a parenthesized list of values, numbers, and in some places, these numbers are so-called not a number, missing values, right? That's how you'd programmatically specify a non-existent number, right? You have to fill in some value. Now, these parenthesized expressions, these are tuples. Tuples have a particular order associated with them. So here we have an array of tuples. We have the first 4 tuple here, the second 4 tuple there, the third 4 tuple here, and the fourth 4 tuple there. So we have an array of tuples, and then we give it our column names for these tuples. And whenever you construct a data frame from tuples, that each tuple represents one of the columns worth of data. And so here you'll see 0, not a number. Oh no, I misspoke. It represents a row worth of data. So you have 0, not a number, -1, 1. 0, nan, -1, 1. The next row here, we have nan, 2, nan, nan. And so when you construct a data frame, you can construct it from a dictionary, you can construct it from a list, you can also construct it from tuples. But when you construct it from a tuple, it's a little bit different. You don't specify the columns, you specify the rows. Once you specify the row instantiations, you also have to give it the column labels. And here, columns equals list, that returns back an array of these strings A, B, C, and D. Does that make sense? Any questions? No? All right. And so here, when you do the interpolation, you have to specify the method. And what the interpolation does, it goes down each one of the columns, and you can change the interpolation to the rows from the non-default behavior. But in this case, with the default behavior, it goes down the columns, and it assumes a straight line with the endpoints, and then fills in these missing values, assuming that everything is linear, right? And so in this case, if we start at 0 and we go to some other value that's missing, and then 2, some other value, it assumes it's incrementing by 1, which is a linear function. And so it fills in 0, 1, 2, 2, right? Here, and it's not perfect, we have not a number. And because this is an endpoint, the 0th value, it doesn't know what to do. So it just leaves it as not a number. Here, we have the endpoints, -1 and 4. So if it's a linear increase, it says, okay, well, I have 4 entries. I'm going to say -2, -3, -4, and fill that in. And so linear is not the only way you can interpolate. There are all sorts of options for the interpolation. And again, its purpose was filling in values under a certain assumption for what these missing entries are. And so you can move along different axes. You can move along the rows, or you can move along the columns when you do this interpolation with the appropriate uh, direction and axis specification. Any questions? No? And we're running out of time, so let me end with a little bit of demonstration in the Jupyter Notebook, and then we'll pick back up on Wednesday with more Jupyter Notebook, as well as a little bit more about data frames. So let me exit PowerPoint, and let me minimize that. It's not letting, oh, there we go. What just happened? All right, so let me bring up the Jupyter Notebook. Let me reshare. PowerPoint kills all the shares, usually. Let me share the notebook, and we'll spend like 2 minutes on this and then end. All right, so here we have a Jupyter Notebook, and I have my imports, and I have some constants in the next cell. And I'm going to go ahead and read CSV, and I'm going to call it CSV file. I didn't call it DF, right? Go figure. And so let me go ahead. Let me run my imports, run that, and that note is just for me. So let me insert a cell, and I'm going to say CSV file head, show me the first 5 entries. Okay, so we do that, and I get the first 5 entries of this data frame. So let me create another cell, and I'm going to go ahead and say age information, and I'm going to slice out CSV file, and I'm going to take age. Let me do it the other way, age, all lowercase, and show that to you. So if I do that, it says, nope, there's an error, a key error, right? And so as I said before, that the keys are case sensitive. So let me change it back to age with a capital A, and let me just rerun that. And we will see, chug, chug, chug. It should pop up. It's not that many items. Hello. Let's try it again. Still churning. I guess the slice out of 891. Come on. Oh, yeah. Duh. That's right. Sorry, just kind of brain hiccup for age info. Let's show you what this is. It's a series, and it's just the default index 0 to 890, so a total of 891. And you'll see here all of the entries for the age field. And so you'll notice it says not a number for some of the entries, right? So we'll say age info, fill not a number with age info dot mean, right? So we go ahead and we can fill all those entries that are not a number, missing entries, with the mean, just like you did in the spreadsheet. So now let's say age info, and we'll end with this, histogram and bins. And since age, actually, we don't know what the age goes from. So let's say age info min, the minimum age is 0.42. So someone was like a third of a year old, 4 months, and age info max was 80. So let's set the age from 0 to 100. So histogram, age info, hist, bins equal 100. So we'll get histogram representing all the ages from 0 to 100. And there's our visualization. And so its power is in all the APIs we have. So that's time. We'll pick back up with this next time. Hopefully the network will agree more with us today. And I will see you all on Wednesday.